There we go. I will begin with a word of prayer. Heavenly Father, we thank you for this day. And again, I just thank you for these students, Lord. I just ask you to bless our work today, Lord. In your name I pray. Amen. So we talked about the fundamental group. And so we're back on that again. I should probably say more about the connection between homology and homotopy. I can say something about it, but I don't know. You know, it depends on how much abstract algebra you've had. And even if you've had all the abstract algebra that we offer here, it's not really something we talk about. But there is a certain technical sense in which homotopy and homology are related. Something like this. Homology is an abelianization of homotopy. So whatever that means, there is a connection. Homology groups are abelian by their construction. They're quotients of vector spaces. So in contrast, homotopy, the fundamental group, can be non-commutative. And in fact, an example of a non-commutative fundamental group is given in this very section, although the calculations are not fully revealed here. So you have to kind of use your imagination a little bit. It's not like the full gory details of that non-abelian fundamental group are shown, but I think a good amount of work is done towards getting us to the place where we need to be to understand them, at least on the surface level. And so this section in Gamelin is very interesting in the way it's written. He's doing two things at once. And so I'll try to follow along. And the basic idea of the section is to prepare to calculate the fundamental group of the circle. But it turns out that the idea of the calculation generalizes. So what he does, rather than just doing the circle, he kind of goes bit by bit and generalizes. It builds the general theory alongside the calculation of the homotopy for the circle. So it's kind of a nice idea, this parallelism in the discussion. I like it. I thought it was fun to read. Let's see if I can get it on the board here. So last time, of course, we ended by talking about induced homomorphisms, right? And I don't really want to put that on the board, but what we talked about was if we have a mapping from one topological space to another, right, then the F sub star gives us a homomorphism from the fundamental group of one's topological space to the fundamental group of the other topological space, provided, I think we needed connectedness, right? Or for the fundamental group to be to be defined without reference to a point, I think we needed that is it path connected or connected? I can't remember. Path connected, yeah. But in that context, where the fundamental group without reference to a point makes sense, then F lower star maps fundamental group to fundamental group, and it's a homomorphism. If F is also a homeomorphism, if it's a continuous topological map with continuous inverse, then that's actually an isomorphism of fundamental groups. So what that means, of course, is that if we can calculate the fundamental group for one topological space, and we can calculate the fundamental group for another topological space, and those groups are not isomorphic in the sense of abstract algebra, that would give us some, rather indirect evidence that those spaces are not homeomorphic. So, and the same is true for the higher homotopies that are described in the next chapter. These are data that we can calculate for topological space that give us what are called topological invariants. A topological invariant is something that if we look at different topological spaces which are related by homeomorphism, then that homeomorphism will preserve that topological data, whatever kind of data it might be, whether it's a number, like a Betti number, or an entire group, right, that will be preserved under the F sub star mapping, the homotopy group. or homology, right? Homology is also transferred by homeomorphism. But let's see here. So that was section 4. That brings us to section 5, which is on covering spaces on page 124. So let me start there. So I'll try to move along here fairly fast because there's a lot to say in this and the related material. But as he says at the start, we want to compute the fundamental group of the circle S1, and this will be aided by the exponential map. And so he says to calculate the fundamental group, pi 1 of S1, we study map. And the map we're going to study, it's P, that is a mapping from the reals to S1, right, given by P of T equals to exponential of 2 pi I T. I wrote the exponential like that so you can see it better, all right? So this is the map that allows us eventually to calculate the homotopy of the circle, all right? All right, so let me give a definition. This is the first example of this definition that I'm about to state, all right? And there's some kind of indirect thinking in this section, all right? So you got to be prepared for it. Let E and X be topological spaces. And P be a mapping from E to X. All right? An open subset U of X is quote unquote evenly covered by P. If the inverse image of U is a union of disjoint open subsets of E. Disjoint union of, what was it? Disjoint union of open subsets of E. All right, great. Each of which is mapped homeomorphically by P onto U. All right. I'll draw a picture that will elaborate on all these things I'm saying in just a second, okay? The map P is a covering map, all right? If P maps E onto X, all right? P is a covering map, all right? If it's what? If P maps E onto X, and what else? Each X in X has a neighborhood, has an open neighborhood evenly covered by P. In this case, we say that E is a covering space over X. All right. All right, let me just take our medicine. I had still more to define. Eventually we'll draw a picture, make all these things hopefully come together. So I've talked to you guys about this before, but what's P inverse of X? Or to be more pedantic, P inverse of the singleton containing X? We had a name for this kind of inverse image. It's called a fiber, right? This is the fiber. Fiber over X via P. Yeah? He says, it is evidently a discrete subspace of E. What's that mean? What's a discrete subspace of a topological space? Let's just leave that question open for a second here. And he says, according to the definition, each X in X has an open neighborhood U such that P inverse of U is homeomorphic to what? P inverse of X cross U. I'm not sure if, I guess that's right here. He says, I'm sorry here. So each X in X has open neighborhood U such that P inverse of U is equal to P inverse of X cross with U. Well, homeomorphic, not equal, but I should say homeomorphic. Homeomorphic. And he says, furthermore, the subsets of P inverse U that are mapped homeomorphically onto U are called sheets of P inverse of U. So this is the disjoint union of sheets. Those are the sheets of, well, I guess, curses. I guess those are supposed to be over here. To be careful. If U is connected, all right, then the sheets of P inverse U coincide with the connected components of P inverse U. Then sheets of P inverse of U coincide with connected components of P inverse of U. All right. Oh, finally. Got through these 2 paragraphs of definitions starting this section, but they must all be said. All right. And I think it's important not to hurry them because we really need to understand these definitions to understand anything that follows. Yeah. But so his picture, to help understand this, is to think of R. I mean, I like the picture he uses. His picture is, think of R as the helix. Right? So this is a picture of R. And then down here, of course, you can think of that as the circle. And P is that map. In the sense that, let's see here. Well, this is just a visualization. I mean, you could just write R as a line. I mean, there's another visualization that you could do for you. You could just think of R as like a line, and you could think about the circle down here, and you could just say that T maps to e to the 2 pi it, right? I mean, you could do that, just a different picture. But there's somehow something nice about this visualization of the reals as a helix, because it captures the relation between the different points on the reals and where they're attached to on the circle and what the fiber is over a given point on the circle. I mean, this helix picture allows us to sort of cheat the algebra. And when I say fiber, you think vertical fiber. I take this point, and you maybe immediately think about, oh, it's these points. Those are if this is x down here, then this discrete spectrum are forming P inverse of x, right? I mean, but in that current format, it's still kind of a drag. If I say x is equal to e to the 2 pi it, like that, then you can actually give a formula for the fiber over that x. What is it? Yeah, I'll start with the t. T is definitely in there, right? Because t maps to e to the 2 pi it. That's the definition of p. What else maps to x? Right, because the exponential is 2 pi periodic. Oh yeah, plus the integers, right. That's the thing, is if we had e to the it, then we'd say like t plus 2 pi times the integers. But as it stands, just t plus, let's say, m, right? Such that m is in the integers, right? That would, and here's the proof, if you don't believe me. If we do p of t plus m, what do we get? E to the, well, I'll use exponential of 2 pi I t plus m, right? And since I know you guys are not all super well versed about complex exponential, I'll write it down again. This is cosine of 2 pi t plus m, right? Plus I times the sine of 2 pi t plus m. But that's the thing, is we know sine and cosine are 2 pi periodic, right? And so likewise, the complex exponential, the imaginary exponential in this context, is 2 pi periodic, which is to say that I can rewrite this, of course, as cosine 2 pi t plus I times the sine of 2 pi t. And that's nothing more than e to the 2 pi it, also known as x. So I've just shown that p of t plus m maps to x for arbitrary integers m, right? So the fiber over x is essentially a copy of the integers, right? In my clumsier linear picture for the reals, if this is my t, right, the fiber over t doesn't look so neat. It's just t, and then over here, t plus 1. and then t plus 2, and then t plus 3, and over here there's a t minus 1, you know? So like the picture of the fiber, if we envision the reals like this, it's just not as exciting, right? So there's something visually cool about looking at the reals as being that helix, because it allows us to kind of to visualize the reals as being kind of squashed, right? Like almost like a slinky that's somehow compressed into a single coil. That's the covering map, that squishing. All right, so I think I have said enough about the fiber that maybe that helps. So what does this discrete mean? Discrete means that every point in the space can be surrounded by an open set in your topology, which intersects just that point. So the points are isolated in that sense. And discrete topology on a subspace. Every point is both open and closed in a discrete subspace, discrete subset. Yeah. So you're saying that with respect to the subspace topology, a discrete set has the discrete topology for itself. Oh, is it? But that's a good question. So I think I feel like I have the sense that we've been here before and we're having this conversation again. But I think that seems like a very good homework problem, right? How do you define discrete? Is it safe to say that however else you define discrete, that a discrete subset is a subset of a topological space, in which the induced subspace topology is the discrete topology for the subset? Because that is a slightly different thing than I'm saying, which is that a discrete space is one for which every point in the space can be isolated. But I bet they're equivalent. Huh. I should go on. That is a very. I should go on. Tempting. Think more about that. But okay, so I think I've explained the fiber, at least for our central example. All right. What next? Sheets. What are these sheets? What's that mean? So what does an open set look like in the circle? If you pick a point, right? Here, I'll just try to picture it here. What do? We evenly covered. It's evenly covered. What's that mean? If the inverse image of U, a subset of X, is evenly covered, if the inverse image of U is a disjoint union of subsets of V, each of which is homeomorphic to U via P. So here's a picture. I'll pick on the same point, right? Here's a U down here. All right? Just a little, think about intersecting the circle with a disk in the plane, in the complex plane, the intersection of the circle with a disk. That gives us a typical open set, at least an example of an open set, which contains X. What's the inverse image of that? Or in my other picture, what's the inverse image of that? I mean, I'll do it here. It's easier. Right, in the helix picture, it looks something like it's this little bit right here, right? Then it's this little bit right here, and this little bit right here. And those are the sheets, right? In some sense, they're like a copy of U, a stack of copies of U, right? If we were looking at like a two-dimensional picture instead of a one-dimensional picture, the word sheet might even make more sense, right? If you can imagine this idea in like a two-dimensional picture, if imagine your topological space is two-dimensional, and your covering is something kind of more like a ramp, right? It might be that you're actually literally looking at like a sheet, a literal sheet above the thing. Okay. Harder for me to draw the picture. I'm happy to have this to draw, but that's the idea of a sheet. This disjoint union makes sense, right? In other words, these are disconnected, right? I mean, they're disjoint union. Anything else to unpack here? Is that good? Any questions? Why is the fiber a discrete subspace? I think that has to do with the disjoint, assuming that P inverse of U is a disjoint union. I mean, we're assuming, was that your question? Or? So we've said that every point in X has an open neighborhood which is evenly covered, right? That means that the inverse image of that neighborhood is what? It is a disjoint union of open subsets of E, each of which is homeomorphic to U via P. So, I mean, the fact that the sheets are homeomorphic to P is essentially by definition here. I mean, you can ask the question, how do I prove that the inverse image of, so here I'm claiming that the inverse image, I guess I should put down specifically the claim here for our circle map, but my claim is that the inverse image of, and he has more details in the book, but I'll just be a little bit more vague. Let's look at, where was I looking at? T, right? T? Is it T that I want? Oh, X. That's not what I want. I want U, P inverse of U, but I want the U. What do I want? I have a picture of U, but how would you write that formula? We're talking about P inverse of what? Of e to the 2 pi I t, or 2 pi I. I shouldn't just use t there. I should say something like, I need some other letter, theta, such that theta is what? It's swinging around angle t plus or minus an epsilon, right? I mean, I can look at a neighborhood which is, it's centered around t for the sake of discussion, right? That will suffice. I mean, that definitely gives us a neighborhood which is evenly covered as long as we don't go too far, right? If we go too far around U, it won't be disjoint anymore, right? Because it'll join back on the other side, and then the inverse image won't be it'll be the whole stupid helix, right? Which would not be a disjoint unit. So anyway, getting to the point here, t minus epsilon less than theta less than t plus epsilon, something like that, yeah? Yeah.
One of the homework exercises from a previous section, I think, was talking about the retraction of all of like R n plus 1 onto the nth dimensional sphere, basically. And I'm wondering, that's where the idea of having all of these, like the fibers
Yeah, so I guess what we're discovering in this discussion is that retraction's not a covering map.
Yeah, I don't think it is a
Right.
covering map. I just think that's kind of unintuitive in a sense. To me, that seems like it's hard to follow.
You think retractions are kind of dark magic?
Well, it seems that they should qualify as covering maps. Like when
Oh.
the intuition of what's going on with a covering map, it seems like why would that not qualify?
You feel like a retraction should be called a covering map?
Sure.
Okay.
Something like that.
There must be a good reason to distinguish the terms, though, I suppose. Maybe we'll discover as we go on through this section what a good reason is. That's an interesting comment. I kind of see what you're going there.
Actually, I have one. No, I guess, yeah, no X would have an open neighborhood.
I think we define retraction in a little bit, so like that's coming, but we're not quite there yet. I don't think that's happened yet in the book, has it?
I don't know. It was in one of the exercises.
Or is it just in exercises? Is it never? Because I have read exercises, like you asked me about those, Emily, and it didn't dawn on me to ask myself the question, when are we talking about retractions in class? I guess the question I should ask is, are we talking about retractions in class? And if so, where? Well, it talks about contractible spaces over here in section 7. So, that means somewhere in there retraction is introduced. Well, I guess that doesn't have to be. We had different. We'll get back to that. Let me continue. Yeah, sure.
I guess one of the unintuitive parts is that it seems like you can have a domain that is too big to have a covering map. Because if you take the example of S2 and R3, like R3 we can't have a covering map.
Okay, let me. You say S2 cannot, it seems, have a covering map.
Well, I think it can have a covering map, but the covering map.
Not in R3 though, is your point.
It can have a covering map in R3, but you have to map from a subset of R3 to S2. So instead of mapping from all of R3 to S2, what if I have a bunch of concentric spheres that I have in R3?
So in all of R3, you feel like you have to replace it, like you need to, if I can draw a two-dimensional version, here's your S2, right? And so the E you're thinking of is like this.
Yeah. See, now, because then all of because now you have a disjoint union of open sets. We're only talking about specific shells. Whereas if you want to map all of R3 by dividing by the norm of all of these different points, you don't have a covering map anymore because the shells are too close together for them to be disjoint unions. But if you have
Very good.
discrete shells, then you can have a covering map.
I really like this. This is a very nice idea. I know what you're saying. See, what Jonathan's saying is, if this is the sphere, and you look at the retraction, which let's call it R let's call it P, just to be really offensive to the current nomenclature. But the formula, P of x equals to x over norm x, has a lot of trouble when x is equal to 0, because, division by 0, still frowned upon even in here. But otherwise, what does it do? It takes the point in R3, or Rn, and it replaces it with its unit vector. So this is a general mapping which will take Rn with the origin deleted and contract it, or retract it, to, I don't know what the correct lingo is here, but it's a retract of Rn with the origin deleted to the n-1 sphere, right? n-1 sphere is the set of unit vectors in that space. A retract is, by definition, a continuous mapping from a space to a subset of that space such that that subset is fixed under the retraction. So what happens to this formula when you feed x a unit vector? Nothing. Something with length 1 from the origin just sits there. Just nothing happens, right? But everything else gets pushed down to that. And if I look at the inverse image, though, of a point here, like here, x, to use the same lingo that we were just using, in this case, an open set around x in that, let's just think about the 2-sphere for a second. An open set around x in the 2-sphere would look like what? It's, you know, something like that, right? And what Jonathan is saying is if you look at the inverse image of that, it's a cone. It's a cone because it goes to the origin, right? And it just keeps going. And the thing is, if you look at that cone, right? Let me call this thing here U. If you look at P inverse of U, it's not a disjoint union of sets which are homeomorphic to U. Because you can't separate the slices. There's a continuum of them. You know, if you take what you want to make the slice and you go epsilon up or down, there's no way you can isolate that slice. Oh. Say again, Kang? You said that there's still...
I mean, those sets are still homeomorphic to U.
You mean this slice that I drew, or do you mean the entire cone?
I mean, each slice that you have, like,
the intersection of the cone with the sphere of radius, whatever that is, just to be specific, right?
so each slice is like the intersection of some sphere with the cone. It's still, I think it's still homeomorphic to the open set U on the sphere, but it just, those slices are not open in topology. So I think that's what the problem is.
Ah.
Wait, why are they not open then?
Because in R3, open things have, open balls determine,
So if you consider the subspace on those slices, it's have the same, like it's homomorphic to the open set.
I mean, replacing R3 with your onion space, okay, I think it fixes the problem because the topology on the onion space makes these, first of all, it makes them disjoint, and second of all, it makes them open. So, okay, so I think what we can take away from this discussion is if you want to build a covering space of a sphere in a somewhat silly way, take your unit sphere and just make a stack of larger radius spheres on out to wherever you want to go.
But I mean, those slices are not
This,
because it's it's just flat, and the open set obviously is more like a ball.
oh, but I'm not saying R3. I'm saying that that set of the onion, the infinite onion, if you want, with the relative topology from R3. I think that would be a covering space for the sphere. Yeah. You notice that the geometry behind that initial picture is not direct. Like, this is a mnemonic to understand the map. I think that's important to say because if you have the idea that that's something directly geometric, it could be very troubling as a student if you're also looking for that picture necessarily in other contexts. I mean, finding the picture is helpful, but maybe it's not possible for the other thing you're looking at. Maybe you have to fall back on the abstract idea of what a covering is. But okay, let me go on. So the inverse image here is what? So the interval union what? That's this one, right? I mean, this is this. But there's many, many more, right? So also t plus 1 minus epsilon to t plus 1 plus epsilon union da da da. There's got to be a better way to write that, right? I mean, the claim is that that's isomorphic to what? Essentially z Cartesian product with minus epsilon to epsilon. Because the inverse image of x is essentially the integers. Up to homeomorphism is the integers, and the where the u is, well, I guess that's still a slight abuse, but that's still a slight abuse. But it needs to be a curved version of this to be most directly. I don't know. What's the best way to write this stupid thing? I mean, I could go more set theoretic on this directly. What would this be? Union over m in the integers of t plus m minus epsilon to t plus m plus epsilon. There you go. It's that. You thought of a more obscure way to do it? Don't tell me. No. No, tell me. I'm just kidding. That's what this class is for. Seriously. Oh, yeah. I like, it seems reasonable to say that this is by definition, right, the integers plus the interval. But that would make some real analysis instructors grimace. So be careful. We should say this in secret. All right. But if this expression has a meaning, surely it should be this. All right. Anyway. Okay. Well, I've spent entirely too much time on this, I'm sure. Let us go on here. The next thing he talks about is the covering space for a, let's see if I can fit this picture in. I think I can safely fit it in over here. Fine, I'm going to do it. I'm going to do it. So he's like, what about the figure 8 space? The figure 8 space. And so his idea here is that you can form a covering by basically doing a helix over the 1, and then at like certain points attaching a circle. And just like the helix picture, this actually extends down below the circle, but we don't want to draw that. And it extends up and up and up. We also don't want to draw that. But if you look at the figure 8 space, right, the fibers, well, some of them, it depends on what kind of point you're talking about, right? But like here, this would be, you know, again, this sort of discrete spectrum of points. And then over here, you know, something like that, I don't know. So here I'm drawing P inverse of Y. Over here is P inverse of X. I guess the question is, what happens? I mean, you want to ask the question, what about the place where they're glued, right? Well, you can kind of see what goes on there as well, right? I mean, he's given a name to that. He calls the place where they're connected at if this is one of those smash 'em up roller derby deals, does this have a name? Like, what's the place where the cars crash in the middle? Does it have like a special name? You guys better do your research before Jimmy Johnson gets here. You're gonna be embarrassed, you know. I personally won't go to that convocation because I'm not a racist. Let's see here. That joke does not need editing. Can be understood by everyone. All right, let's see here. I stand by my joke. Anyone who likes NASCAR is a racist. Let's see here. I probably should explain the joke now. People who like NASCAR are fans of something called racing. This is a joke about cars. This is not an insensitive comment about a general population being all racist, in case you're worried. Oh, the time is soon coming. We can't even make such jokes casually. All right, it's probably already here. E0 is, what's he do there? He's labeled that little E0. All right. He says, if we unwind the loop of E naught, so this whole contraption, this whole deal is E naught, the covering space, right? This whole, I mean, R is E here, right? Or you could view this as the covering space, this helix. That's the covering space in that case. So this is the covering space of the figure 8 space. And he says, if we unwind the loop of E naught touching little E naught, then we obtain another, what? Another covering space E over X as suggested in the figure appearing towards the end of the section. Oh, curses, I didn't want to read that right now. Oh, that is not helpful. I wish I had not read that paragraph right now. That is not what I want to talk about. I'm sorry, we're going to have to leave this picture just to be vexing. I'm trying to think what if I can add anything to that at the moment. Maybe I can't. Let me go on to the next example. The next example is projective space, n-dimensional projective space, Pn. All right. And so how did we define n projective space? You guys remember? Yeah, it's a quotient space, right? Yeah, Pn, which was defined to be the sphere, basically the n sphere mod this equivalence class, where equivalence is the identifies antipodal points. This may not be how we actually defined it in here. I think we defined it a different way, but this is yet another way of defining n-dimensional projective space. so just to draw a picture, basically, and I'll do S2, which is of course a subset of R3. And so the equivalence is that, you know, if I look at, say, this point, then I don't know if I'm drawing it worth anything, but attempting, this is x, this is minus x. X is equivalent to minus x, right? So Pn, Ppn is the equivalence classes like this, right? But these are kind of silly equivalence classes, right? Because they're really just, they're not singletons, they're doubletons. Sorry, that's not really a word. But here it is. I mean, no one writes it this way, but if you wanted to be stupid and like find the most clumsy notation possible for projective n space, there it is. All right, it's pairs of antipodal points. Now, but he says, you know, what we should look at is the quotient space obtained from the unit sphere by identifying antipodal points. And he says, let P from the n sphere to Pn be quotient map. So what does that do? In other words, what is, so P of x is equal to what? What's that? The equivalence class of x, aka this pair of points, right? And he says, okay, so if x naught is a point in Sn and epsilon is small, we can look at the, like, you know, like a little open set around x. All right, so what's that look like? So I'm getting lost in, his V is in Sn. I'm sorry, let me write it down rather than trying to think. V is equal to x in Sn. I'm not sure I can draw a picture of this worth anything. I mean, he's got a picture in here, but I'm not sure what to do with it at the moment. Norm of x minus x naught less than epsilon. And here we're assuming epsilon 0 is small enough. Well, I guess I can attempt a picture of V. What does V look like here, roughly speaking? Well, that's the thing, is the sphere provides a picture for both P2 and S2 at the same time, if that makes sense. So if I'm thinking of V as being in S2, that is a kind of open set around, let's say, well, I'll draw another picture over here. Right. Picture not awesome, but so, you know, this is some kind of, here's x naught, right? I'm saying that this is V, all right? And so the center point there is x naught. That's a subset of S2, right? He says U equals to P of V. What's U equal to P of V? Right, it's this, and then also down here as well, right? Like the P of V is essentially V union with what kind of stupid. Minus v, I suppose, would be a reasonable and, I mean, I think it is actually that, right? Fair enough. King is he's saying that I should take my set and replace it with a set of sets. In particular, I should say it's the set of x such that x is in V. That is, after all, what P of V is, which is a subset of the equivalence classes of collections of points which are obtained by mapping V under the quotient map P. Blah. True. But it's more fun to visualize it that way. Anyway, what's the point of all this? There surely must be a point, or two of them. The point is that P inverse, well, you can see, it's visibly clear, right? That P inverse of V is really a disjoint union of this and that. And he says both V and minus V are mapped homeomorphically by P onto U. What's U? Oh, U is P of, oh man, look what I've done. This is horrible. No, that is V. This is altogether U. Good night. The point here is that P inverse of U is V union with, now you won't object, right? Now that's actually the honest to goodness truth, right? I mean, V union with minus V is the inverse image of this set of cosets, and that is indeed a disjoint union. What I'm trying to say is that we can pick a neighborhood of x naught small enough, right, so that it's evenly covered by how many slices? 2. Right? So this is a so-called 2-to-1 covering map. Every fiber consists of 2 points. If you say a blank to 1 covering map, you can measure the whateverness of it, if you will, by the number of things in the fiber. So I don't know what, is that an infinity to 1? It's you know, whatever you want to call that. But, all right. Furthermore, products. So this next thing is nice. Products of covering spaces are covering spaces. All right. And, time flies when you're having fun, yes. So he points out, if we look at, for example, Tn, which is the circle, Cartesian product with the circle, Cartesian product with the circle, n-fold times the so-called n-torus, right? This is covered by Rn. And the projection map that, let me erase this. Oh well, if I kept better track at the time, I wouldn't have gotten into that one. So the projection map here, let's see, or so like T1, T2, Tn. So it has to map onto